And here we go. We have liftoff. Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, roger, planet.
Water towers fly! Yes!
Tango down to nominal.
Flight downside SPD off. Bring in SPD off. Off. It's orange!
Orange 45. Oh my god! Oh my god!
Decollage.
Look at this!
Put that in the big bag, Signal.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
This methane would be igniting in the flare, correct?
Yikes. You good? Sure. We don't need any more of these.
All right, folks, you know the drill. John Galloway with NSF here. Time for another NSF Live today. If you haven't already been watching our streams, testing happening down there at Starbase, a little bit of a mini wet dress rehearsal. So I imagine some number of you are coming straight out of the cryogenic testing down here at Starbase. Going to be talking about a little bit of a different mission here today, actually multiple types of missions, because we have a fantastic special guest with us. Please welcome to the show, Dr. Alan Stern. We'll get him on there. There we go. Dr. Stern, how you doing?
And well, happy Sunday.
Happy Sunday. Thank you so much for taking time out of your Sunday to join us here today. We've got some cool stuff to talk about.
Yeah, I'm looking forward to it.
All right. So folks, watching here, if you've seen awesome imagery of Pluto, Dr. Stern has a little bit of involvement with those images you may have seen coming from Pluto. The New Horizons mission, Dr. Stern is the principal investigator for New Horizons. And then also just like breaking news this last week, you'll be doing a space flight of your own coming up here. I think it's currently scheduled for early November as part of Galactic 5, right?
It's 11 days from now.
11 days from now. Are you already in New Mexico? Are you on the way there? Or?
I'm in Canada right now, and I've got to get to Boston for a New Horizons team meeting. We have 3 a year, and then I'm going into Mexico right after that on the weekend.
All right, good deal. So just sort of like come sliding in, and you have your experiments all set up for that space flight that you'll be doing, huh?
I think we're good to go.
All right, good deal. We have a lot of different stuff we want to talk about because you do so many different things. I asked while we were starting up the show, like, oh, which mission should we put? And you're like, I've done 30 missions. Couldn't fit all of those on the ticker, but you've done a lot of different stuff. But let's get started with New Horizons, and we'll talk about Galactic 5 coming up here, because the big news with New Horizons is that there's more New Horizons coming up, right?
There is. NASA saw fit to continue our Kuiper Belt exploration, which is what we were sent there to do. We're currently extended through 2028 or 2029.
So that was a thing you sent New Horizons out there. I mean, it launched in 2006. It flew for years and years, and then it did the flyby of Pluto. It continued past another object out in the Kuiper Belt, and then it's still going. The spacecraft doesn't just stop when you're done with it. It still has a trajectory it's following. So it's just sort of hurtling out into deep space right now, right?
Yeah, the spacecraft is like the Voyagers on a hyperbolic trajectory, leaving the solar system. Even if it died, the spacecraft itself has all this forward speed, enough to escape the solar system and travel into the Milky Way galaxy. And so every year it's farther and farther away, and it'll be in interstellar space sometime in about a decade.
About a decade. So what's it? That's part of the thing. Like, the mission was supposed to go for a certain amount of time, right? And then, all right, we're going to shut down the mission. The space probe is going to keep going. I think nobody wanted that to be the case, right? Because the spacecraft was still alive. It still had all the energy we put into it when we launched it, and we did flybys and the gravity assist and that sort of stuff. But it was still going out there. And in fact, it's sort of going in a trajectory, and we don't really know what's in front of it right now, do we?
Well, we know that we're going to be in the Kuiper Belt for another half dozen years,
right?
With opportunity to continue to study Kuiper Belt objects. So far, New Horizons has studied almost 36 different Kuiper Belt objects after the close flyby of Arrokoth. We're looking for another close flyby target, but we study others in the distance using the telescopes and cameras on board. So
Gotcha.
we're pretty busy, and we're doing things that can't be done except by a spacecraft in the Kuiper Belt.
Gotcha. So it's not like, all right, New Horizons has flown out here and it's approaching Pluto. Great, we got awesome images of Pluto, and then we flew by, we look behind us, we see Pluto some more, right? And then it moves on to another target. It's sort of the target that's on the trajectory that you can give it a little deflection, like a little nudge to get closer to that other target. But while it's flying through the Kuiper Belt, you're not sitting there twiddling your thumbs. You still have science to do, right?
Well, we do a variety of different science. We do unique astrophysics that can only be done because you're very far from the sun.
Right.
We do studies of the outer environment of the sun's cocoon called the heliosphere. And we've got much better instrumentation for that in most cases than Voyager does. And we do these studies of the Kuiper Belt, which have never been done before. And frankly, there's no spacecraft coming to follow us up. There probably will be someday, but nobody's even designing it, much less building it or getting it to a launch pad.
So as you continue on here, the instruments on the spacecraft are still functioning. You can still control the spacecraft. You can point these instruments to different places. What sorts of things is the spacecraft actively doing right now? Like, are you looking at specific objects? Is it coasting along while you're gathering, let's say, radiation data or something like that? Like, what specifically does New Horizons do these days?
Well, there are 13 different scientific investigations that are going on. And then there's a choreography of mission operations that goes on top of that to send up the software that runs the spacecraft a few weeks worth at a time. Those are called command loads.
Right.
Then after we collect data, we put it in flash memories on board the spacecraft. They're twinned solid state memories on the spacecraft. And then we have to choreograph the downlink with the Deep Space Network. So all that's going on. At some points in time, we're only studying the radiation and heliospheric environment. Other times we're looking at Kuiper Belt objects, we're looking at dwarf planets, we're studying cosmology and extragalactic astrophysics. And then we're doing a variety of other things, studying the local interstellar medium, looking back at Uranus and Neptune to study them in ways that you can't from the Earth. And there's more. So it's complicated and it's a lot of fun. And we're going to milk it for everything it's worth because there's no other spacecraft out there that can do this kind of work.
Absolutely. You've like you said, you built the spacecraft. It's launched out there. It's still going. You still have control of it. You can still run the scientific instruments. I can probably say it wouldn't make any sense to just turn it off. Turn off the lights on Earth. Just let the thing coast out there. You might as well get science back from it, and I guess experience from operating it as well, right? As long as it's still kicking.
More importantly, we were sent to study the Kuiper Belt. We're now there. It's an enormous structure, much larger than the planetary system out to Neptune. We're about halfway through it, just barely halfway through it. And because we were purpose-built to go use it once we got there, even just from a fiscal standpoint, the U.S. taxpayers invested nearly $1 billion to get us to this point. And that's about 98% of the cost that it will take to finish the Kuiper Belt mission. So we spent 98 cents out of every dollar to get here. Sure makes sense to me to spend the last 2 cents to actually get the goods.
I think that makes sense. Let's talk a little bit about how that works, right? In order to extend the mission of the spacecraft still needs to be healthy. So right now, New Horizons is still healthy. Is there anything like the lights that aren't quite blinking in the right order, or any little hiccups that have occurred that you've had to sort of work around, or is it still firing on all cylinders, I guess you could say?
Well, the spacecraft's very healthy, and so are the 7 scientific instruments on board. In fact, it's very hard looking at the engineering data to even tell that it's aged since the week we launched it.
No kidding.
Look at the voltages and the currents and the temperatures, and they're just flat lines. They're really boring. We've had a few lessons learned. We've had a few hiccups along the way, but nothing's broken. Everything's working. We have power, fuel, and comm range to get out to mid-century.
No kidding.
And my plan is to make sure that we get everything we can out of it.
So let's talk about that. Like, one of the things that limits the life of a spacecraft sometimes is the power and the fuel, right? And we can look at New Horizons here on the screen, and we don't have the massive solar panels that we see on a lot of this. And this is one of the primary things of New Horizons, because it was going all the way out there. It is not a solar-powered spacecraft, right?
No, it's nuclear powered, like the Voyagers and the Pioneers, because we're out where the sun is thousands of times dimmer than it is down here in the inner solar system at 1 astronomical unit. It's not practical to use solar arrays. For one thing, they would be too cold to really work out there.
Right.
Even if you could make them work, you would need acres of them to create the power that's required, as opposed to that little nuclear battery, basically the black cylinder that's projecting from the spacecraft. That's a spare from the Galileo and Cassini orbiter programs that we procured and then had fueled by Los Alamos National Lab and the Idaho National Lab up in this cool place called Atomic City, Idaho. And it's got plutonium on board. Plutonium is in a matrix called plutonium dioxide. There's enough of it to run the spacecraft out to about 2050, with a little less power every year because there's a half-life.
Yep.
So it doesn't generate as much power each succeeding year. When we launched it, it was about the equivalent of 4 60-watt light bulbs. We're now down to about 3 60-watt light bulbs, and we can keep running it down to about 1.5, maybe closer to 2 60-watt light bulbs, and that's quite a ways off.
Okay, so that's just as the fuel degrades, it's supposed to. It's got the half-life, like you said, but as it sort of puts out its energy that you then harness to power the spacecraft, it doesn't matter if you're right next to the sun or if you're way out in the Kuiper Belt, right? The the nuclear fuel, I guess, the nuclear energy creates the same amount of power, maybe some thermal considerations between the two different locations, right?
That's exactly right. Yeah.
But you couldn't do that with solar panels. Like you said, you would have had to have acres of solar panels, because once we get this far out there, in order to catch enough photons to create the electricity to run the spacecraft, they'd have to be massive, right? But
massive, in fact, to get it launched onto this trajectory. The device is called an RTG. That stands for, it officially stands for radioisotope thermoelectric generator. I just call it the really terrific generator because it makes missions possible.
So as this goes out, from a power perspective, which is one of the limiting factors that'll limit the life of a spacecraft, right? You're good to go through, you said 2050 almost, right?
That's right. Yeah.
Gosh. So that's one of the things. In power, is it going to be the sort of thing like as the, I guess the light bulbs sort of dim down a little bit, you get down to 1 light bulb? Are you going to have to disable instruments or do some power management where it's like, we can't run everything at once. We can turn this on, then send this message.
We already do that.
Okay.
But it's going to get more and more extreme with the years, just as Voyager has. Eventually we'll get to where we have to take turns between scientific instruments. We can only run one at a time.
Yep.
But right now we still have plenty of power to do all kinds of extra things. For example, right now we can send data back at twice the rate of a single transmitter because we have enough power to power both of our 2 transmitters at the same time. They transmit in opposite circularly polarized signals, and the DSN can receive them at the same time. So we're really talking on 2 different data lines at once whenever we're sending data. But there will come a point in a few years when we don't have the power to do that, and we'll be down to 1 data line. That's an example.
No, that makes perfect sense. And again, it's all about the terminology used was like squeezing everything you can out of the spacecraft, and it's still operating just fine. Another limiting factor for a spacecraft's life is fuel sometimes. So do you have like a consumable fuel on the spacecraft, and how are those levels looking?
Yeah, we have a consumable. It's called hydrazine.
Okay.
Monopropellant. When we launched the spacecraft, we filled the tank. We filled it in Florida over the Thanksgiving holiday in 2005 in the clean room before we put it up on top of that big Atlas V to launch it 2 months later. We've now expended almost 90% of the fuel to get us across the solar system through 3 different science flybys at Jupiter, Pluto system, and Arrokoth, the Kuiper Belt object. We have more fuel than it would take to do 1 more flyby. But we have to nurse it. I call myself the fuel hoarder in chief. And we can run the spacecraft once we're done with the Kuiper Belt, and we just want to do what's called a spinning mission, where the spacecraft is gyro stabilized, spinning at 5 revolutions per minute. We can run for 15 to 20 years on the last kilogram of fuel out of the 78 that we launched with.
No kidding.
So we have a few more kilograms, more than a few, but we have a little bit of fuel left for further Kuiper Belt work. And then at some point we'll hang that up and it'll become a Human Spirit mission.
Gotcha. So, with the fuel, like, what are the different things the fuel is used for on the spacecraft? Is it like, say I want to visit another object, so I need to deflect my trajectory a little bit. I assume that that's one of the uses of fuel, and another one may be attitude control, or
Those are the two and only those are the only two uses. Every
Well, there
time
you
we
go.
fire a thruster, whether it's to turn or to spin up or spin down
yeah,
or divert trajectory or just refine trajectory, that costs gas.
Yep.
And
So right-
I haven't seen any gas stations in any of the images out there. I think we're pretty much got the only tank we'll ever get.
the only tank you'll ever get. Hey, maybe someday somebody will catch up to it and refill the tank and let it keep on going. I think it's a stretch goal for a future space mission. But hey, do you have, like, right now, it's on its parabolic trajectory, it's leaving the solar system. I would guess, I don't know if this is the answer, but you don't need to redirect the trajectory any right now. Like, it's just sort of going out there ballistically, and there's no big maneuvers planned. Like, say you were trying to do a gravity assist or something. There's not really the opportunity to do that out there, is there?
Well, there's no gravity assist because there are no planets along our path that are farther out.
Yep.
We did get a gravity assist from Jupiter. We got a tiny gravity assist from Pluto as a part of the flyby. It's just a byproduct. But we won't see any more of that. We're slowing down very slightly every year as we pull out of the sun's potential well, out of the sun's gravity. That's very secondary. We only need to use the propellant on board for targeting flybys and for pointing the spacecraft.
Gotcha. So when you say pointing the spacecraft, it's like attitude control, like making sure the dish is generally pointed back towards Earth and these sorts of things, right?
We can keep it pointed back at the Earth for 10 or 20 grams of propellant per year.
Oh, wow.
That means if that was all we wanted to do, we could run this thing a century on the available fuel and more. But there's a lot more we want to do, and that costs gas. And so on top of pointing it back to the Earth, we have to point it at scientific targets. And every time we normally operate the spacecraft in this gyroscopically spinning mode, 5 RPMs.
Yep.
But whenever we want to stop to do a stop spinning and point at things along the way or for a flyby, it takes gas to take all that angular momentum out to stop, go to 0 RPMs.
Yep.
And it takes gas to do the pointing or the flyby. And then you have to spin it back up. And so we keep track of all that with a software tool, which has been calibrated over the years that we've been flying. It works really well. And there's a certain amount of stuff that we can do on the fuel that's available. We just husband it as best we can.
Makes sense. If I could ask a technical question real quick, there's no control moment gyros or anything like that aboard where you could use electric power to point the spacecraft, are there? Or is fuel the only way to aim the spacecraft?
On New Horizons, we made the decision not to include those. For one reason, we were trying to be as light as possible to go as fast as possible.
Yep.
But also, at the time that we were designing New Horizons in the early 2000s, we knew that virtually all of the control moment gyros fail in fairly short order in a matter of years, not decades.
Right.
So we knew that even if we included them, that by the time we got far out, they'd probably be disabled and we'd have to operate without. So we just went without as a cost-saving and mass-saving measure. And frankly, it simplified the spacecraft operations because we didn't have to create the software and control systems to do both things. We just do it purely on fuel.
That makes sense. And I guess maybe we could say when it's doing its 5 meter or its 5 rotation per minute, was it? Spin, it's almost
5 RPMs.
5 RPMs. It's almost its own big gyro because it's stabilizing itself with that angular momentum. That's why you put it in the spin, right?
And when we do that, the thruster valves, we'll see, we can see them in telemetry. We'll see 1 or 2 thruster pulses a week.
A week.
It takes almost no gas to keep
kidding.
It.
Can I ask, how do you measure the fuel that's on board? Like, is it a pressure gauge or did you weighing it? Do you just, every time we fire the thruster, we keep track of how much we use? Like, how do you know how many kilograms are left?
Right. Good question. Well, first, it's weightless. So to weigh it, we would have to fire the engines and spin fuel. That wouldn't be a very smart way to go about it.
Yep.
But what we do is we use pressure transducer. We actually have two of those as an A side and a B side. They're redundant. We use pressure transducers that correspond through a real simple mathematical relationship to how much fuel is left.
So it's just it's reading the pressures in the tank, and there's no way for that tank to change pressure besides the fact that you've let some fuel out of it, right?
It can change with temperature too.
Temperature.
But we measure those temperatures and we take that out as part of the calibration.
Does that happen? Like, I guess it can't be in the shadow of anything out there, right? There's nothing for it to be in the shadow of. But as it goes further away, do the temperatures decrease noticeably?
Well, they did a lot at first because we were close to the sun and really baking like any spacecraft at the Earth's distance from the sun. Within a year, we were out to Jupiter's orbit. The sun was 25 times fainter, much smaller contributor. Another year, and we were out past Saturn's orbit. And after that, the sun was down to 1%. Now it's just a few tenths of a percent. So the changing distance from the sun hardly affects our temperature.
Makes sense.
Of course, the stars are constant. So the inputs to the thermal situation are pretty constant now. The only thing that changes the spacecraft temperature is how much of the avionics we have on any given time. So when we're doing a flyby and everything's going on, all the bells and whistles, the spacecraft heats up a few degrees bulk temperature compared to when we're running it quiescently. But the whole range of variation is pretty small.
Gotcha. And it's well understood after operating the spacecraft for so many years, you have a good handle on what you see as you see all these different temperature sensors coming in and stuff
we
like that.
We have a thermal engineer on the project. He's been with us since he was in on the design of all this. It's brilliant design. His name's Jack Urkel, and I call him the Maytag repairman because nothing ever changes.
Nothing ever changes. Nice.
We don't have to call Jack very often.
Oh, no. So as we're going out here, right, the spacecraft is still healthy. You still have control of it. You're still talking to it. I've heard some news recently that, the DSN is getting overloaded. Oh, there's not enough antenna time on the DSN. New Horizons is in deep space. It talks with us via the Deep Space Network. Is New Horizons getting less antenna time because of other missions, or is it just something you schedule?
Well, I think your question needs some background.
Okay.
The Deep Space Network is a shared facility. So, we share it with other missions. That's been the case since the DSN was born 60 years ago.
Yep.
And what missions need the DSN vary with time because new missions are getting launched and old missions are finishing up. And it's also a question of where you are in the sky. Because if you can imagine, there are now a couple dozen spacecraft scattered around the solar system. Some of them are on fast orbits. For example, they're at Venus or Mars. And so they're changing their position in the sky pretty quickly. There are others like New Horizons and Voyager that are just in one direction and they're not going anywhere. And so which ones are in our part of the sky determine which ones we have to share with. And so when Mars is on our side of the sun, we have to share with them all those Mars spacecraft in that flotilla at Mars. When Mars is around the other side, we don't have to compete with those guys, but we worry about all the other ones. Anyway, it's a big shared network, and it works pretty well. Each station, there are 3, has many, many antennas. Because we're far away, we require their biggest, most powerful honking antennas. They're 70-meter diameter antennas. So they're the better part of those dishes, the better part of the size of a football field.
Yeah.
And when we're using one, it has to point directly at us and nowhere else, and we're the only one using it. But we get a bunch of time every week. And of course, if no other spacecraft existed, we could get a lot more data to the ground. But the whole nature of it and the way we designed the mission was with all of this in mind. So it works fine.
That makes sense. I think that's the context that maybe a lot of people have missed when they may have heard about this. There's news stories and, oh no, the DSN just doesn't have enough room. But I didn't even think about, all right, if Mars is over here, then that part of the sky is sort of busy and we only have so much time where the antennas can see that part of the sky, right? Versus Mars. Go ahead.
What's really important for, I think, listeners to realize is that as we're proliferating our ability to do space flight, and more nations are getting involved in planetary exploration, and now private companies are getting involved, The DSN is not going to have enough capacity. It's going to have to be built out, or they're going to have to be private services that supplement it. We already have lots of private networks for ground stations for Earth orbiting, and now even cislunar spacecraft. I think the day will come, won't be too far away, when we see the first commercial services for interplanetary communications.
It'll be a good problem to have when we get there. Like, there's so many interplanetary spacecraft. Now there's a market to provide those services. Like, that's a good problem for us to have, I think.
There you go.
I like having that many spacecraft out there. Let's talk about what is the future of New Horizons here, right? Is there a target specifically that you think you might be able to fly by? Are you searching for these targets? And how do we search for targets like this? Do we just have ground-based telescopes that are looking for holes in the sky that we might want to go investigate? Or how do you even look?
I'm going to try, but I think you asked 6 separate questions.
I did.
If I leave part of that out, you're going to remind me, aren't you?
I will. It's okay. Sorry.
So here's the way we do that. The very best way to search is not with New Horizons itself, because although it has perfectly good cameras and it's closer to everything out there, the data rates back to the Earth are the limiting factor. And we couldn't really do the search because we're too data starved.
Right. So
our primary tool are large ground-based telescopes. And the very best one for our purposes is one of the largest in the world. And it's a Japanese telescope run by the Japanese ground-based astronomical agency, NOAA. It's called Subaru. Just like the car, Subaru is the Japanese word for the Pleiades, the constellation Pleiades. It's a roughly 10-meter class telescope. But the thing about it is there are some little bit bigger telescopes that are online. This one's got the best megapixel camera with the widest field of view, which means it's the most efficient.
Okay.
For searches like this, because instead of having to do a lot of soda straw views searching, this one's got a big field of view. You can do it all at once. Actually, technically, it takes us 2 fields to do it all. But Subaru is our primary tool, and we use it every year many times. And when the weather's good, which is most of the time, we detect new Kuiper Belt objects. We have so far detected hundreds of Kuiper Belt objects along our direction of flight. And we've studied dozens of those. Many of the ones we find are not close enough to be able to really make an important study of. We can't get the signal to noise. And every one that we discover, once we have enough data points tracking it, we can get its orbit. When we know its orbit and our orbit, in the computer, we can figure out how much fuel or delta V it takes to divert from our orbit to an intercept that would take us directly to that target. For example, for Arrokoth, which is the KBO that we flew by after Pluto, it took about 55 meters a second of delta V, which corresponded to about 18 kilograms, if I remember, of propellant, of the hydrazine, to go get it, right? We fired the engines back in October of 2016, and divert maneuver takes us to an intercept on January 1st, 2019, okay? So what we do is we look for new Kuiper Belt objects. We find them all the time. When we find one that's within our remaining fuel supply, we're going to set off a bunch of fire alarms, tell NASA. They're going to send the money to staff the project back up to flyby levels.
Right.
And we're going to go do a flyby of something twice as far out as Arrokoth, because by the time we get there, we will be twice as far out. And we may never find that. In fact, we have pretty good models of the Kuiper Belt, and we know what's where as a function of distance. We're finding it's more extended than we thought, which is good because it gives us more time to find something. And but even though it's very far out, we also find that the odds of getting something are really low, unless there are big surprises that we don't know about in terms of the number of Kuiper Belt objects much further out. The odds are about as low as, as an NFL team that's down by 4 points. They got 50 yards to go. It's the last play of the game, and they're going to throw a Hail Mary.
Okay.
The thing is, the odds are against you. That's why it's called a Hail Mary, right?
Yep.
But sometimes they score, and there's an upset.
Yep.
And so for New Horizons, we're going to look under every rock. We're going to look with the biggest, baddest telescopes on Earth. We're going to use the best ones in space. If anything's out there that we can reach with our fuel supply, we're going to know it, and we're going to go there as long as it's within our fuel reach. You just have to stay tuned like the rest of us, because we may not know for 5 more years if we can find it or not. Because every year, as we get farther out, things work against us because they're fainter and fainter as they're farther out. But things are working for us because new telescopes in space and on the ground come online with better and better capabilities. So that's like a spy versus spy war. And we'll just see how it turns out. I'm on the edge of my seat.
Gotcha. Let me see if I can repeat a couple things back that you just said there. You used the term looking through a straw, like a straw search, right? And I think when you said that, you're talking about the Subaru telescope, and if it was a really narrow field of view that could zoom in on just one thing, that's great if you have a target to look at. That's like looking through a straw. I don't have any straws here on my desk, but if you were to look through a straw, you could just see a little teeny tiny part of the sky. And that's fantastic if you are looking for something specific, you know where it is, you want to point the telescope there and get fine detail. But if you're doing like a big survey, like you said, they have the big
want to cast a wide net, right?
Cast a wide net. Yeah, absolutely. So that Subaru telescope is casting this really wide net, and it's looking at a big patch of the sky. Does it, I assume that it looks at the entire sky, but does that telescope get tasked to specifically look for new horizons, or is it just looking at the whole sky and you can use that data?
Subaru's big wide field is just a couple times the size of the moon as we see it on the sky.
Oh, wow.
So
okay.
It's still zooming up, and it needs to. But by comparison, the field of view of the Hubble Space Telescope is something like 100 times smaller. So you'd have to do 100 Hubble images for every one Subaru image if they were the same size telescope with the same cameras out back, same efficiency.
Okay.
So Subaru just lets us do the search much faster, right?
Gotcha.
Now, there are some new facilities coming online. One is called Euclid. It's an ESA mission, European Space Agency mission, just launched. It's a wide field telescope in space. That's an advantage. We're going to launch another wide field telescope in space with an even bigger telescope, about the size of the Hubble, in 2027. When I say we, that means NASA.
Sure.
Right? That's called the Roman Space Telescope, named after Nancy Roman.
Yep.
Very important 20th century astronomer. There are other tools. James Webb Space Telescope, although narrow field, can go deeper and look for fainter, smaller things or farther away things than any of those others that I just mentioned. There's a National Science Facility, that's the other NSF. They have a telescope coming online called the Vera Rubin Observatory that's going to be doing motion pictures of the sky. So it's a real wide field facility. And we don't know which of these is going to snare something for us, but if there's something out there, one of them's going to get it, and we're going to go after it as long as it's within our fuel reach.
Makes sense. When you work with these telescopes, does it work like you say, hey, telescope, could you look at this part of the sky for new horizons? Or are they inspecting these parts of the sky and your use is one of the many uses that data may have?
So that's a great question. It is not like let's say an Earth resources, an Earth surveillance mission where you just go into a database and pick out, I just want to look at Moscow because I want to look at the Russians,
right?
Or whatever it might be. No, in our case, we have to win telescope time, either win or buy telescope time, and then specifically point the telescope with a specific instrument on its back end in a specific mode on specific nights with good enough weather conditions to get our data. Our data might be useful for other people, but we are pointed just where New Horizons is going and nowhere else. And they don't normally point there. No one does, because the sky is enormous and all these fields of view are tiny. So we have to go get our own data.
Makes sense. It's not like you just go to kuiperobjects.wikipedia.com and here's all the information about that, right? You're specifically looking for new things. Is New Horizons, I have to ask, is New Horizons currently sort of going directly away from the Earth, or is it crossing the sky from the telescope's, field of view? Like if the telescope's looking, is it like chunk, 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 or is it just sort of looking up New Horizons' tailpipe?
New Horizons is headed in one specific direction.
Okay.
The coordinates on the sky are called right ascension and declination. That's like respectively longitude and latitude in a way. We're going at one direction, and it doesn't change. It changes so minutely that effectively it doesn't change.
Okay.
So we have to look in that direction only to find the Kuiper Belt objects that we might fly by or study.
Trying to like line up, we've got the NASA eyes visualization here with New Horizon and its trajectory. And I'm like, where's Earth in the background? Because you could go to see, like if you were looking up and I guess the Earth wasn't turning, which is why it would move across the sky, right? Is New Horizon just sort of going straight away from the telescope, or are you looking across the sky? But it is
straight. It's going almost straight away. And
primarily straight away.
Varies from straight away is because the Earth moves around its orbit from one side to the other every 6 months. That makes a little bit of parallax. But except for that shift, which is now about plus and minus a degree per year from one side of the Earth's orbit to the other, except for that, we just look in the same direction over and over, but we look farther and farther out with succeeding years.
Makes sense. A silly question maybe, but can any of these telescopes actually image New Horizons in any way, even as just a glint across the sky, or is there just not enough energy bouncing off New Horizons now?
No, the answer is no. It's not a stupid question at all. I wish we could. It'd be great to take a selfie, right?
Right.
Yeah. But the smallest things that we can see out there are about the size of a county. They're tens of kilometers across. The spacecraft is less than 2 meters across. So there's not a prayer that we can see it directly with these telescopes.
Gotcha. And that comes to searching for targets as well. Like you need, I guess the targets have to be of a certain size for us to be able to detect them with whatever telescopes we have or coming up in the future. You're not going to see a softball-sized Kuiper Belt object. Kuiper. I don't even know if I'm saying that correctly. It's just Kuiper?
I think it's Kuiper. It's
Kuiper.
A Dutch word, and I don't speak Dutch either, but people say Kuiper.
Kuiper. We'll go with Kuiper. You're not going to find a softball or a basketball or even a truck or a ship floating in space. You wouldn't even see something of that size. It's huge land features. Like you could see a mountain that was floating in space, I guess, right?
Be a big mountain.
Be a big mountain to see it. No kidding.
Yeah.
So what other, like when you looked at extending the mission here, right? We know we wanted to extend it. Was it the sort of thing where you sort of had to give and take a little bit? And did you have to give other people time on New Horizons or let other people look at missions? Or is it still controlled by your team? Like, help me understand how that sort of works. Is it another team now?
There was some drama, but here's the bottom line to all that is that normally every 3 years, every NASA mission that's achieved its basic objectives, what's called a prime mission,
right,
has to compete. They compete with one another for limited funds, and NASA decides which ones are a good deal, which ones are right side up from a value standpoint, because there's always too many good ideas for the available budget. So which ones are producing really important data for the budget that they need? And so there's that competition every 3 years. And the proposals that get written are very thorough, complex, scientific cases, but also you have to justify every bit of your budget, every salary that's on there. You have to justify the spacecraft's health and its expected continued health, and many other things. And you send those proposals in, and teams of experts look at them, rank them against one another and against some objective standards. And then they come back with a consensus report. And in our case, the consensus report was very positive. It had 23 major strengths. That's a criteria for NASA, number of major strengths. And then it had one major weakness. So that had to do with how many data points we took on each Kuiper Belt object we passed by to study its light curve. A pretty narrow single concern compared to the big panoply of 23. That's the way to do it. Right at the top, scoring, and those scores have to do with everything, even down to, are you mentoring the next generation of space scientists? So they look at everything. They look at your productivity. They look at your technical health. They look at your plan. They look at the scientific work. They look at the budget, and I could go on. So all the missions get ranked up. We were right in the middle of the ranking, not the highest, not the lowest. I think if we had a flyby target we'd identified, we would be at the very top, but we haven't found it yet. So we're in the middle. Then there was a bunch of time spent back and forth about what we should be doing going forward and what the budget level would be. And most of that got sorted out here a couple of months ago. And so now we know that we're extended until 2028 or 2029. That's basically until we leave the Kuiper Belt. It's very clear that the highest priority objective, and rightly so, is to look for another flyby target. And along the way is to do good science, because if we never find a flyby target, we have to have something good to show for the money we spent running that spacecraft while we were looking from the ground. So we're going to do all those things, and we're going to make an A+ in every bit of it. And with a little luck, knock on wood, we'll get a flyby as well.
Makes sense. Can I ask, and tell me if this is like a number that gets released, but continuing to operate New Horizons, what's the largest expense to keep the spacecraft running? I mean, it's not like you have spacecraft repair cost. You can't do that. You can't refuel it. There's no spacecraft specific,
almost
cost.
Everything gets spent on salaries.
On salaries. So people.
We have to buy new computers as they wear out for the ground system, for the mission control, for example, and the Science Operations Control Center. But we're not buying parts and things like when we were buying, building the spacecraft. But we have engineers and scientists and flight controllers and project managers, about 50 people total that work on New Horizons. Now, let me contrast that. When the Voyagers were flying across the solar system, their teams were 10 times as big, 500 people class. So we're a skeleton team by comparison. And every person on the project, myself included, only spends a fraction of their time on this project. I typically spend a quarter of my time.
Really?
On the project. And I work on other things. And the flight controllers and the engineers and the other scientists and the project managers they wear multiple hats on different space projects all at the same time. So we've got it down to about as inexpensive an operation as you possibly could do. So we have 50 people, but not 50 full-time equivalents.
Full-time equivalents makes sense.
We have, 15. I'm making the number up. It's in that vicinity. If everybody works a quarter or a third of the time, it's like 15 full-time people to operate this billion-dollar spacecraft and its ground system and do all the science to make discoveries from the data.
Gotcha. And that's just the operation of the spacecraft, because then once you gather that data, then it's provided to the larger scientific community and other people can do different comparisons and research and that sort of stuff.
We get paid to skim the cream off the top, because NASA, of course, wants to make sure that the data are ones and zeros in databases are worthless unless human beings look at them and make sense of it and make discoveries.
Right.
And so we do that with the data as it comes to the ground. And sometimes others go back and look in more detail. They have more time, or they'll see it from a different perspective, and they'll make further discoveries. Like people are now milking the data from Pluto to learn things that we've gone on past that, and we're working now on the Kuiper Belt part of the mission.
Yep. That makes good sense. And it's not like the data comes in and you do one report, then you delete everything. That's not how science works anywhere.
Try not to ever delete anything.
Try not to ever delete anything. Nice.
We're real careful about what we delete.
Nice. Another part of that is experience, like mentoring the upcoming generation of, I'm going to use the term scientists and explorers, right? And
engineers and flight controllers and project managers and all those skill sets.
Yep. Absolutely. So part of that is folks can be involved with this mission as a part of what they do, right? And they can gain experience, they can gain skills here that they'll use or improve for the future. Is that sort of how it works, right?
Yeah, but another example is we have a program within New Horizons where we put a little bit of budget aside. It's called PDP, and that stands for Personnel Development Program. And every year we select, there are people compete, and we select individuals who want to learn a new skill set. They're generally junior and mid-career, but sometimes there are even people late career who say, I've been let me just say a geophysicist as an example, working on Kuiper Belt objects in Pluto, and I really want to learn about it, scientific instrumentation, or I want to learn about project management, or how to lead a mission scientifically. And then we assign them a mentor, and they go do on-the-job training, not reading books and looking at slide decks or listening to YouTube videos, but actually they shadow a person and they get handed more and more responsibility during the course of their mentoring, so that they're actually not just talking the talk, but walking the walk.
Makes
and
sense.
learning to do it. And then they get a graduation certificate that they were trained in that, mentored in that area by somebody who's,
Doing
on
that,
the project to do that.
Yep.
And then they can take that to, in some cases, to do new things or at a higher level on other projects. In some cases, for example, our new deputy project manager on New Horizons, we have two of them, and both of them, Cindy Conrad and Gabe Rogers, had other jobs on the project. They mentored under project managers and became deputy project managers as a result of that PDP.
Makes sense. I think a lot of people don't understand how important that is specifically. It's not like, I'm an engineer and I'm doing this one mission, then I'm done. Like passing on our experiences for future missions, and more importantly, the future people who will make those missions happen, is a huge part of anything that we do. Just gaining and building and retaining that experience, right?
Absolutely. Otherwise, we get a lot of people that are book smart but don't actually know how to do it.
Yep.
And my view is we all benefited from teachers and mentors in our past. For those of us who are in the leadership positions, we should be paying it forward.
I think that makes good sense. It's important, and people just don't understand how important that part is, right? All right. Well, here's a couple questions. I'm getting lots of questions from the folks here, and I'm going to pull a couple apart real quick. I got a couple technical questions. Yeah, I got a couple technical questions. This one we'll start with a softball, right? How long does it take to transmit images data to Earth? And does that change the further out it goes? So you have some sort of bit of data, right? I guess it's not really a photo. Well, you could send photographs, but you have some bit of data. Is that like an hour of transmission time to get one photo back, or how does that break down? And is it getting harder to get
more
stuff
complicated than that?
Okay.
There's 7 scientific instruments. Each one produces different kinds of data.
Mm-hmm.
And they produce them at different rates, not just because they're different instruments, but also because they each have different modes and selectable or tunable parameters on the instrument. But what doesn't change is that the spacecraft only has a transmitter of X watts. In our case, 30 watts of transmit power. Not 30 kilowatts like an AM station somewhere. 30 watts. At the other end of the line is this giant DSN antenna that's listening, right? And although occasionally they'll have upgrades, more or less our data rate is controlled just by the size, the power of our transmitter and the size of that receiving antenna. But as we get farther and farther and farther away, that data rate goes down because the signal is more and more diluted by the distance. It's harder and harder to hear it. So when we launched New Horizons, we literally had data rates of 100 kilobits per second from this small antenna on the spacecraft. Now our data rates are more like 1.5 kilobits per second. We're very far away. How long it takes to transmit a data set depends upon several things. At 1,000 bits per second, how big is a given image, and how much are we willing to use JPEG compression to make it smaller? If you make it smaller, it's not free. You don't get the same details out. Some cases, that's just fine. In other cases, you have to send the raw data product. So we typically send about 100 megabits, which is, a little more than 10 megabytes per week back to Earth through the DSN.
Wow.
We just went through a very intensive period of scientific data collection in August and September, where we put several gigabits on board the spacecraft, new stuff, and that's going to take the rest of this year to get to the ground. So this is a mission that's all about patience and delayed gratification.
So did everybody just hear what Alan said? 10 megabytes? Was that a week?
Yeah.
That's like you loading one image in your web browser. An image is probably, it could be 5 to 10 megabytes these days. And so you load, I think the YouTube thumbnail was 2 megabytes for this show, right? So you could send 5 YouTube thumbnails.
Right. But we have, first of all, we have some tricks up our sleeve. Here's an example.
Okay.
When we use our high resolution imager, it's called LORRI. It creates a single image. That image is about 12 megabits. Okay. It's 1024 by 1024 pixels, and each image has a 12-bit stack of ones and zeros that tell you its brightness. But when we go to send that to the ground, first thing we can do is we can losslessly JPEG compress it. That gives us about a factor of 2 typically. That's a big help. But we can also say if I took that image to study one Kuiper belt object in the field of view, then I only need the little box. I don't need the whole 1024 by 1024. I need maybe 100 by 100 box around the Kuiper belt object, and I'll just go zero in on that, take that much smaller subset of the image out, and send that to the ground. That's only 1% as large, but you get all the important data. Yep. And we do that all the time. So we make very good use of the bandwidth that we have. We're transmitting about 10 times faster than the Voyagers. But still, we're very, very far away. And with present technological capabilities, this is what you get.
Yep. Makes sense. It's interesting. Like, a lot of people don't understand. People are used to having fiber at home, and they have their broadband internet and all these things. And spacecraft don't have that same luxury. Like the way you explained, we're going to just focus in on this subset. We're not going to download the whole image, right? We're just going to download the important part at a higher resolution so we can get that important data back. Instead of, it's probably the right way to say it, is being wasteful, right? You can't be wasteful. You have to manage.
And with radio wavelengths, it's hard to focus as well as we can with visible light or infrared light.
Yep.
And that's why a lot of spacecraft in Earth orbit, and now even cislunar missions, are moving to optical communications, which have much higher data rates because you can focus the signal better. And an important step forward in that is a mission that you might have heard of. It just launched, called Psyche.
Right.
Psyche's up on a 6.5-year journey to get to this metal asteroid, but along the way, it's testing the first interplanetary optical data
link
system. Yeah.
Yep.
And if that works out well, then that should become a commodity a decade from now that we can use so that future missions, whether they're inner solar system or outer solar system, will have much higher data rates. That'll be very important, even for human exploration missions to Mars.
It's literally like if people watch The Expanse or whatever, and they're like, oh, we're going to send a tight beam. Like, we are building those technologies right now so that you can still higher bandwidth, higher bit rate information across the solar system. Like, we're on the cusp of deploying and testing out those technologies right now.
Guaranteed, when James Tiberius Kirk actually walks this planet, he will be living in a time when they look back on the 2020s, I predict, and they will say, the 2020s, that's when Star Trek began.
That's when it started. I like it. It's like goosebumps. Like, this is the time that we're alive, y'all. There's so many different things that we could talk about. I want to make sure we talk about your upcoming spaceflight with Virgin Galactic as well. Let me see if I can grab a couple more questions about New Horizons, then we'll move on to that. Has there been anything that you've learned from New Horizons, or I guess what's the top thing that you've learned from the execution of this mission that you would like to apply to a future mission? Is there like one thing that you're just like, man, that's a great thing we learned, we should put this in future missions?
You know, I'm going to take my right to change your question, or at least give you a different answer than you're looking for. I'm not going to pick one thing.
Sure.
Because, you know, on the technological side, this spacecraft really broke the mold for miniaturization and low power electronics. The entire 7-instrument payload, which has about 1,000 times the capability of Voyager, runs on 28 watts, half a light bulb.
Wow. That's
one example. We also more or less made spacecraft hibernation practical on New Horizons. It saved a lot of money. So those are the examples of the technological breakthroughs. But just as important, we did New Horizons we built it, we designed it, built it, tested it, and got it launched in half the time of Voyager on 1/5 the budget. So we figured out how to do this much more efficiently and make it work, by the way, because it doesn't do any good if it fails after all that.
Yep.
We did all that for 2 dimes on the dollar compared to Voyager. Which means we can use those lessons to do more planetary exploration. and to lower the bar for what it costs to do individual missions if we do them the same way. So I'm very proud of both the programmatic advances we made and the technological advances that we made. And then, of course, we revolutionized our knowledge of the Pluto system and the Kuiper Belt, which is what we were, sent there to do. A lot of missions talk about rewriting the textbooks, and that's true. But in our case, there was no textbook.
There was no textbook.
Everything we knew about Pluto would fit on basically one piece of paper before New Horizons. So we wrote that textbook from scratch.
That makes sense. It's just, I remember when the images were coming back from Pluto and some of our icons or even Pluto icons, and you see the heart and you see the new, hey, look, there's Pluto imagery on the screen. Nice. Just what we got back from that, when previously it was a little chunky blur in the sky, right? That in and of itself, I hope this doesn't come across the wrong way. That in and of itself, just seeing those images sounded like the entire thing was worthwhile just to get those back. And we got so much more than just that, right? But just the inspiration of being able to see that, I shouldn't say the farthest little thing out there in the solar system, because there's even more that you're still going to. So just the fact that we got that back was
and
amazing.
Not so little in Pluto's case, about the size of the United States.
Yep.
Take a while to walk across it.
Planet sized, no big deal. Anyways, the just seeing what came back was such a huge deal for me personally, right? So let me grab just one more question here and see what we got. Easter eggs. I think we'll skip the Easter eggs. Wasn't there like a coin or something that you used to balance the spacecraft? Was that New Horizons?
Yeah,
and you had
you're
to
remembering well.
Yeah.
We ended up flying a Florida State quarter since we launched in Florida. That's our Florida State dollar, US dollar, and a Maryland one coin as well, because we built it in Maryland.
Yeah.
And rather than just tack them on the spacecraft in random places, we decided dual use. So there are these fine balance weights that weigh about the same as one of those coins. So we just replaced the fine balance weights in a couple places with the coins. And that worked out really well.
That was the coins. It's not like you just, we put them on there for fun. Like you needed to balance the spacecraft. You needed just a little bit more mass here. So you put them in those strategic locations. The question was actually about, are there Easter eggs or like a golden record sort of thing aboard? I guess
there are 9.
There are 9.
There are 9 of these things aboard New Horizons, not just the 2 coins.
Yeah.
There are 2 U.S. flags. There are ashes of Pluto's discoverer, Clyde Tombaugh.
Yep.
There are 2 CD-ROMs, one with the names of 500,000 people who wanted to put their names on a spacecraft to Pluto and the Kuiper Belt. The other names, pictures, and messages of team members who worked on building New Horizons, a couple thousand people there. I'm losing track if I gave you 7 or 8 or 9 so far.
Close
but you get the idea.
Yeah.
There were a variety of mementos aboard.
Yeah, I specifically remember the coins because it was, we had to balance it and we needed some mass here. And instead of just putting, dumb piece of aluminum or something there was actually a little memento sort of thing.
Want to hear a great story about one of those coins?
Yes, please.
We had to get the Florida coin and we're almost out of time. And I literally stopped with the director of the Kennedy Space Center at a Burger King. And I asked the young people who were working at the cash register to see if they could find a Florida State dollar somewhere in there. They're rifling through. Yeah. And I'm thinking these workers at this little Burger King don't know this thing's going to be launched across the solar system, right? They couldn't find it. We had to leave for a meeting with Governor Jeb Bush, who was then governor of Florida. And we were about to launch it. And I said to Bush, I told him the story. I said, so I guess we're not launching a Florida State quarter. And he goes, I've got some. And he went and got us one. And that's the one we launched.
Nice. Not the one from the Burger King. If only they had found one from the Burger King.
I just thought that was sci-fi to think that some coin from a Burger King will be flying across the solar system and out into interstellar space. Wouldn't that have been awesome?
I would have gone back and been like, oh, by the way, that coin you gave us, it's on the way to Pluto, or just past Pluto or whatever.
There you go. That's right.
Geez. All right. We have some time left here. I do want to talk about your New Horizons. that are coming up here. Galactic, you like that? That was really clever, right? New Horizons, but
That was a good pivot.
Yeah, you like that? Chat, help me out. The next thing that you're coming up here, flying with Virgin Galactic on Galactic 05, doing some suborbital experiments. Let's talk a little bit about what's going to be going on there.
11 days from now, I'm going to fly in space.
And flying in space. And you're not just flying in space for fun. You actually have some experiments you're going to do, right?
Right. Actually, in this case, the crew consists of 6 people. There are 2 in the forward cockpit.
Yep.
There's a Virgin trainer in the fuselage in the back cockpit, and then 3 paying individuals, 2 researchers, myself and Kelly Girardi, and then a space tourist who's also flying.
Right.
Kelly and I are both going to be conducting experiments. In my case, the experiments are specific to a second suborbital flight I'll do, hopefully next year, for NASA to do more sophisticated experiments. This is sort of a training exercise, what we call risk reduction.
Right.
I could be wrong, but I also could be the first person to be sent to space purely to train for future space flight and for no other reason. That would be kind of cool. But even if it's wrong, I'm really looking forward to just doing the work and getting a chance to see our planet from above, and to getting some experience so I can do better at future ones.
Gotcha. I saw, like, I was reading the information about what you'll be doing, and it was mentioning human-tended experiments, which is the opposite of New Horizons, the spacecraft, right? It is not human-tended. These are experiments that humans need to be there to help run. And then also you're wearing a harness, like a biomedical harness, I think it said.
Yeah, both Kelly and I are wearing biomedical gear to measure our physiological response to the high G's on the climb uphill, to the microgravity, and then to the reentry. We're wearing different gear by different manufacturers with different capabilities, but it's the same idea. And you know what's really powerful about these suborbital spacecraft by Virgin Galactic and Blue Origin is that there are a couple of things that are really important. One is they dramatically lower the cost of doing experimentation in space, like factor of 10 level. So it's huge. It's like if cars dropped in price, to a few $1,000s instead of a few tens of thousands of dollars, it would be a game changer. Well, this is a game changer on the price of space access for doing research. And the vehicles fly very often too, so you can take advantage of the lower cost to get a lot more done. But the sneak attack, the best kept secret, which I'll tell you and the listeners here, is that these vehicles, for the first time, put the experimenter in space, which means we get rid of all the complexity and cost of designing an automated system.
Right.
All the testing is required to work all the bugs out, so it's going to work all by itself. And with humans there, we can change the experiment as we go. So this is really the secret sauce, because, in every other science, volcanologists go to volcanoes, oceanographers go in the ocean, astronomers go to telescopes, right? Chemists go in the laboratory. In space, what do? We sit in mission control and we hope that we worked all the bugs out before we launched it. We're now getting to the era where the experimenters can go. It's going to normalize the practice of science in spaceflight, from a mission control to we go to the moon, we go to Mars with scientists, or we go to Earth orbit or suborbital flight and get the costs down, the reliability way up, and we put the investigator right in the environment. And then they come back and they make a better, I think, inspiration for school kids to go study hard things like math and physics and chemistry and be the next generation.
Sure. I got to ask, we talked about getting the experimenter there, right? The experimenter will be there in space. And I wonder where the balance is, because you have a limited amount of time that you're going to be in the microgravity environment, right? And so you're going to have a script of things that you are going to do to accomplish the task in that time, right? But at the same time, you're a human being there with your Mark I wetware up here you're carrying with you, and you can make observations and change things on the fly. For something like this, do you have leeway to change the script if you see something? Or is this more about following the script exactly and then also getting that data that you're gathering via your own senses and then change it on the ground, fly it again, and change up the experiment next time? Like, can you change the experiment mid-gain if you've got a couple minutes to do it?
Well, it's hard on a suborbital flight when you only have a couple of minutes to get the job done, but you can adapt to operational changes in real time. An example being a sun glint might cause you to change which window you're doing your observations out of.
Okay.
That would be very hard to automate, and if you did that, it would be expensive. But for a human, that's the snap of a finger, and you realize what to do, and you make that change. Right?
Makes sense.
I don't have to worry about very carefully designing a cable routing for my ultraviolet camera from its power pack to the different observation sites. I just manage the cable because I got 2 arms and a brain.
There you go.
Done. So there are lots of practical advantages over automation when you put the human in the loop. And that's why you don't find very many automated geological expeditions. You don't find very many automated oceanographic expeditions. You don't find automated laboratories that are run entirely by robots in universities or private industry. It's just better to have the humans there. Finally, in spaceflight, we're getting to the point where the costs are low enough to allow the humans to go with on a regular basis. And the secondary gain of being able to close the loop on the experiments is the icing. Everybody likes the icing better than the cake.
Sure.
It's the icing that really makes us go.
I imagine you already know the experiments that are going to be happening. Can you talk a little bit about specifically what you'll be
11
doing?
days to go. You think I know what's going on?
Yeah, I hope you know, like, what the experiments
They
are
haven't
supposed to
told
be.
me yet.
The ticket's bought and paid for. You just show up on the day of and they're like, we need you to do this. How much can you tell us about the specific tasks you'll perform during the flight?
Yeah, well, we have a set of 7 objectives, and we have different tasks to satisfy each objective. Some of those objectives are purely training and risk reduction for the NASA flight. I'll give you an example. I know it sounds silly, but it's true. I'm going to be very, very busy on the NASA flight. And who's human wouldn't want to look out the window and see the beauty of the Earth, right?
Yep.
So on this flight, we're actually dedicating 30 seconds so that I can do that and kind of get it out of my system. It's
get it out of your system
next time. Right. But much more where, for example, I'm wearing that biomedical harness, which will not only collect real data, but it will tell us about its wearability in the 4G ascent, how well it stays connected to us, and the leads collect data when we're in zero gravity, and then how it does on the entry as well.
Okay.
I'm going to be carrying a mock-up of the astronomical camera and practicing getting from window to window over your seats and onto the next window and stabilizing with only one hand while the other hand points the camera. See how all that works? And we're going to be carefully analyzing the videos to see how many seconds did it take to do each and every task so that we can put as much as possible into the NASA flight without being overly ambitious and falling flat on our face the other direction.
I hate to use the
calibration.
Yeah, I hate to use the term ground truth because it's not really ground truth here, but it's the same concept. Like, you're testing these things out in the field, I guess. Even in the field is a little tough there, but you're getting the truth of how these things will actually work when you want to do it. Can I ask, how are you cued? Like, are you going to have a little earpiece and it's like, bing, you're allowed to look out the window 30 seconds and then bing, start the experiment? Like, how do you know when those timers happen?
That's an important question. There are a number of cues. One thing I was surprised at is that when you're in the cabin of the Virgin Galactic vehicle, there's no clock.
Really?
You'd think there'd be a big clock. There's not one.
Okay.
But in any case, I'm wearing a nice wristwatch that'll metronome every 20 seconds.
Okay.
And tell me what time it is within the sequence. We also have some call outs from the cockpit crew and the onboard Virgin instructor that tell us, time to unstrap. You're at 50 miles altitude, apogee, time to get back in your seats, those things. And I'm following a checklist in this case because it's only a few minutes to get the work done. It all fits on a cuff checklist on my arm.
Just like strapped to your arm.
Yeah, just like the Apollo astronauts wore on moonwalks. Theirs was many pages. This one's only one page in this case. And it's my cheat sheet to make sure that nothing gets left out.
Nothing wrong with that. Do you mark it off as you go? That's you have to marshal a pen and zero-G or just look at it. You're like, you already have your list like strapped to your arm?
Yeah, I'm just looking at it. No marking.
No marking.
Yeah.
So you have
actually,
a couple
if you're interested, I'm going to be blogging over the next few weeks. And the second blog, first and second blog will be out in the next few days.
Okay.
The second blog actually has the checklist in it for those who are true brother nerds who want to really see what it's all about.
Where do we find that? Is that on your website, or where can we find where the blog is going to go?
You'll find it on my social media. For
Okay.
example, Alan started Twitter or
Okay.
X these days. You'll see it on Facebook and Insta, but also it's going to be in the Space Review.
Space
If you know
Review.
that.
All right.
Jeff
Yep.
Faust, the Space Review.
Yep.
Probably going to be on NASA Watch.
Okay.
And there may be some other venues as well.
Good deal. So blogging about your preparation for it. And I guess hopefully not during the event, like you'll be in there in the spacecraft, you're doing a new blog post or whatever. But give us some feedback after you come back again, huh?
There'll be a few after the fact with some lessons learned and some integration of what the experience was all about.
Makes sense. Let's see. We'll see if our moderators can put that link into chat. Just link up Dr. Stern's social media. Twitter's a good place, and I imagine if you have something there, you'll link it out on Twitter. So if you're on X, Twitter, whichever we're supposed to call it these days.
Mm-hmm.
All right, we'll get that link into chat so y'all can click on it and follow along. If you're not already following Alan here, make sure you toss him a follow and keep up with what's going on. Where are you right now with the preparations? Like, I've been out to Spaceport America for Virgin Galactic coverage, and they make a big thing about it's 3 days of training, right? It's only a little bit of training before you actually get aboard and do the flight. You've probably already designed all your experiments before you even paid for this. Like, are you practicing this? Like every night, do you go through your checklist and you make sure you have muscle memory of what you're supposed to do? Or what do you do to prepare with this before you get to Spaceport America?
Great set of questions. The experiments were and the operational objectives were all defined long ago.
Right.
And the training falls into several categories. One is just general background training. I spent 5 years flying F-18 Hornets doing airborne astronomy, and I flew U-2 type aircraft doing airborne astronomy and did polar expeditions and all kinds of things that relate from an operational standpoint of doing similar kinds of things, oftentimes under high time pressure.
Sure.
More specifically, done a fair amount of high G training, flying in centrifuges on F-104 aircraft that simulate the 6G climb up to apogee. Zero G aircraft, done a couple dozen zero G aircraft flights. So from an environmental standpoint, getting familiar with the environments is important. And then there's just a run through of the activities. This is something that the space tourists, there's no equivalent for that.
Sure.
If I was just going to enjoy the view and maybe to do some somersaults, I don't think I'd be training the way that we're training.
Right.
But here we have some objective success criteria, and the customer really cares that we get it done. I'd like to be selected for future space flights, so I'm motivated to get it done too.
Yep.
Right. So we do practice the procedures over and over, and we haven't yet practiced them actually in the Virgin
spacecraft. Yeah. But
starting next weekend, we'll be down in New Mexico and doing that day after day to be ready.
Good deal. When I was out there, one thing that I didn't understand before I was standing next to the spacecraft was that because it goes up there and it does a little flip, right? And it sort of changes it around. So you see the different views out of the windows, and the spacecraft is changing its orientation as it's flying. But the center of gravity, the center of mass, I guess, of the spacecraft is not in the crew cabin. It's actually back where the motor is. And when it does its rotation, it's rotating about the center of mass. So the crew cabin is sort of like bumping you whenever they do that maneuver, and they had to change how they fly to minimize bumping the people that are inside because it wants to rotate around the motor, right?
Right. And so in the Virgin vehicle, the attitude profile is, you're vertical on ascent.
Yep.
And you get the engine cut off, and you're still vertical.
Yep.
And shortly after that, they enable the reaction control system jets.
Yep.
And they put the vehicle on its back, so all the windows are facing down.
Yep.
For basically best view for the tourists, right? You stay that way until the vehicle flies to apogee, and then the vehicle does a 180 and prepares for its entry attitude.
Right.
and feather the vehicle to get the entry configuration correct. At that point, it's time to get back in your seats and then go through the entry and landing.
You get the seat backs and tray table sort of thing, right?
Yeah, and the same thing is true on other spacecraft. That astronauts often see the vehicle rotate around them, and that the positions of walls and things change at different rates depending upon the vehicle and what kind of operations it's doing.
Yep. Makes sense. So as you're going through this, you mentioned parabolic flights, right? And you've been on quite a few parabolic flights. What can you do here on the Virgin Galactic flight that you can't do on a parabolic flight, besides the fact that you're technically up in space?
Well, there are a couple of things. In my case, I'm primarily doing astronomical observations. So it doesn't require on having microgravity. It just depends upon being high above the atmosphere. But for the people that are doing microgravity research, whether it's materials and fluids or flammability experiments or manufacturing experiments, whatever they might be doing, there are two key advantages to these, to the environment. And I'm not talking about the lower cost anymore. I'm not talking about the advantage of having the experimenter. There are two key environmental differences. One is that the disturbance spectrum, the jostling that you get, is 100 times less than on an aircraft flying through the atmosphere trying to make microgravity. So instead of being jostled around at nearly 1/10 of a G, you're being jostled around at a milli-G, 1,000th of a G. So you get much cleaner microgravity, and the fluids and the physics all depend upon that. That's very important. Secondly, on a parabolic flight, the very best you'll ever get in an airplane is about 25 seconds, normally about 20.
Per parabola, I guess, right? You get that much time,
and there's just not enough time in many experiments for the physics or the chemistry to run to completion. On a single suborbital flight, you get several hundred seconds. And so you have not just the equivalent accumulated time of 10 parabolas, but you could do 10 parabolas, by flying all afternoon in an airplane. But you can get the chemistry or the physics to run for 10 times as long. So you collect data you could never collect 20 seconds at a time, because every time you restart, you're starting from zero again.
You have a higher runtime, like your experiment can run consecutively,
and a much cleaner microgravity environment that makes such a big difference.
And the cleaner microgravity is because the parabolic plane is still in the atmosphere. It is not jumping out of the atmosphere. And that atmosphere, even though it's trying to cancel out the rate of fall with the trajectory of the plane, the atmosphere is still moving the plane some. It's not a perfect trajectory, right? It's going to get jostled a little bit, like you said. And when you jump out of the atmosphere, I think we're jumping far enough up that we could call it that it's out of the atmosphere, right? When you're jumping that high where the atmosphere is that thin, you don't have that same effect. I had never thought about that before.
Yeah. So there are a lot of advantages to these suborbital vehicles. There are economic advantages. There are, human in the loop advantages. There are actual physics of the experimentation advantages. In the case of astronomy, you're high up, so you're above the obscuring effects of the atmosphere. You can work at ultraviolet or infrared wavelengths, or there are other types of things you can do as well. You just can't do very well unless you get that high.
And that's the primary thing you'll be focusing on is astronomical observations, I think you said?
Right.
Like the important thing for you is being out of the atmosphere.
How good is the Virgin vehicle for doing astronomy? And if it pans out, then there should be a lot of applications for Virgin to go sell flights, not just to US researchers, but to researchers around the world.
Okay.
These have applications. Astronomers have been using robotic suborbital vehicles all the way back to the 1950s to do this kind of stuff. If we can now do it not once a year, but once a week, and if we can do it for 10 times less price per flight, that's game changing.
And with people aboard as well, with human beings there, the researchers with the experiment, instead of having, like you said, make it go up there and be autonomous, not have the researcher with it. I had never really thought about it that way, but I'm curious. Can I ask, when you do these observations, are you going to be just looking out the window? Like you're going to be shooting the observation through the window that's already on the spacecraft, or is there a special window they're installing for this?
No, we're using the windows that are there.
Okay.
And we're actually taking a space shuttle experiment I was principal investigator for. and looking at the same star fields with the same instrument. The only
Okay.
difference is instead of a space shuttle window and space shuttle attitude disturbances, it's a Virgin window and Virgin attitude. And we're going to see if Virgin can do better or the same or not as well. And
Gotcha.
little things matter in this. So you could calculate a lot of that. You could simulate it in a computer in a sort of perfect world environment. But what we can't quantify are the things like the glints off the wings affecting the experiment, or the microscopic scratches and films that come from the propulsive ascent that you don't have. They're different every flight.
Yep.
And so the only way to really find out is to go do the experiment, bring the equipment, look through the window at the same star fields that we did with the shuttle, with the same instrument, and compare. It's pretty basic stuff, but it's virtually impossible to get the answer until you just go get the data.
Is it the same type of instrument, or is this an actual physical instrument that also flew on a space shuttle?
This
For my
is
curiosity.
This is a literally 25-year-old instrument that works perfectly. That was high tech in the end of the 90s and early 2000s. That has been in a controlled environmental storage all this time. We're using the same gear, the same atoms, right? On Virgin that we flew on the shuttle a number of times.
No kidding. And what you just said is important. It's not that the instrument itself has degraded being in storage for 25 years, and that's going to be a difference in your results, right?
We calibrate that out. That's not even effective. Yeah.
No kidding. So you're flying on the flight with a space shuttle instrument, and you're going to be taking observations out the window partially to see how the Virgin Galactic window changes. And not only are you getting that information for yourself and then also learn about the process and get the experience and that sort of stuff, but that's provided back to Virgin Galactic as well, so they can improve their
we publish the
offering.
results in the open literature, and Virgin can read the results, and the entire research community worldwide can read it. And so it's going to be a benefit to everybody who wants to use that kind of data.
Interesting.
It's not something we give to Virgin at taxpayer expense. We give it to everyone, and then Virgin can come and read it too. And that's to their advantage. They may want to change how they do some things to make it even better.
They could have a different type.
They want to show off how great the data is.
Yeah, they like they could come back and install a special type of window or change the glass on this one thing. And when you're doing these observations on this vehicle,
wiper out on it.
It's some sort of new coating that keeps it in the state that makes it better for observations. All of these things, like I will say, a lot of times we get people that pop through here and on the internet, they have their opinions and like, oh, what's the point of doing these hops like this? But just sitting here talking to you about it for 25 minutes, I've learned stuff that I hadn't even considered. The micro vibrations as you're in the atmosphere, and the amount of time, the run time for a specific experiment, the exact conditions, the way you're propulsively launching, and can we make these observations out this window? There's so much more to it that I think that people just don't understand. So
people are busy. And,
they are.
Thanks for saying that, because it made an hour and a half on Sunday worth my time. I'm glad we could do it.
Well, good deal. We've had quite a few people here watching with us as well. Folks, I've been reading questions. Every now and then I've sort of like put a couple questions into the mix. I don't call out names or anything like that, but thanks all the viewers for all of your great questions. Yeah.
NSF should be at the Galactic 05 launch and cover this.
Careful. Jack is probably, we've gone out to a couple of them. Virgin Galactic has been super nice to us and given us access to help cover these things.
And this will be your first chance to talk to a couple of researchers the minute they come back from their first space flight.
We're going to have to make sure somebody goes out there, it sounds like. No kidding. Alan, Dr. Stern, thank you so much. It's here at the end of our show. You have given, I like to think that I keep track of what's going on, and I read articles here on NASASpaceflight, and just all across the internet. And I try to keep up with things that are going on and understand the concepts, but just here, I have learned new things, and I have more things to consider and to like load into RAM when I'm thinking about these things, right? Yeah. Just having the conversation here with you was invaluable for just an understanding of how these suborbital space flights help us advance what we're doing. Thank you so much.
Thanks a ton. And I'm glad we could talk. It was a pleasure.
Gosh. See, I didn't even
keep doing what you're doing. I love NSF.
Like I didn't even have time to like hold up the book. I got this book when we were at Intrepid. You're Chasing New Horizons book. And I have 2 of them here, actually. I still have the bumper sticker that we got there. My other vehicle explored Pluto out there. I had all these things sitting on the desk next to us. We didn't have time to talk about that. There is a book, y'all. If you want to pick up Chasing New Horizons, the mods have a link they can put into chat. Your website is there as well. Alan, you've got the website that links to the different things that you're working on. But I am super interested in hearing your experiences when you come back from Galactic 05 here. It's coming up in a couple weeks, it sounds like. But I think for now, any parting thoughts, any last things you want to share with folks before we end the show?
I think you covered it really well. I'll just say that spaceflight is one of the important aspects of humanity's future, and we don't know how it's going to turn out, but it's going to be something wonderful. And all of us who put our time into it, either as interested parties or workers, are contributing to that Star Trek future we know we're going to get to someday. So keep doing what you're doing.
Absolutely. Just having conversations like this and getting this sort of information and inspiration in front of more people is part of what drives that, right? So many different people can be involved with this. So many different walks of life, so many different skill sets are required. It's a theme we hammer on all the time, but there really is room in space for everyone. And don't think because, I just do this, I'm just an accountant or whatever. I mean, there's accounting in what you do.
All those skill sets to make it go. Yeah, absolutely. Every one of them.
All right. Well, folks, our special guest today, Dr. Alan Stern, not only from New Horizons, but on the upcoming Galactic 05 flight. Again, thank you so much for spending the time here today, Dr. Stern. Folks, follow him on Twitter. Be looking for the blogs that he talked about, those experiences he's going to be sharing, so you can keep up with what's going on. Take this to heart. If you missed the beginning of the show, you came in the middle, you can scroll back to the beginning. You can learn a little bit more about New Horizons and the extension there that's going to continue providing science and inspiration for years to come. But that's going to be the end of our NSF live show today. Alan, once more, thank you so much. Chat, y'all know what to do. Say thanks to Dr. Stern, and also thank you to our members who make these sorts of shows possible. The font is getting tiny on this screen. We're going to have to do something about the font on this screen. But everybody across the board that makes this sort of stuff possible, we appreciate you. For now, that is going to be the end of our show, and we will see you nerds later. Thanks again, Dr. Stern. We'll see you on your flight.
11 days and counting.
All right. Good deal.
See you soon.
And here we go. We have liftoff.
Propulsion continues to be nominal.
RS-68 chamber pressure looks good.
Doubling up. Roger, Atlantis.
Water towers, fly! Yes! Tango down to nominal.
Flight comes SE off. Bring in SE off. It's orange!
Oh my god! Oh my god!
Decollage. Put that in the big bag, Tingle.
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This methane would be igniting in the flare, correct?
Yikes. You bet. We don't need any more of these.